So drawing a free body diagram. Free body diagrams, otherwise known as FBDs, are simplified representations in a problem of an object, the body, and the force vectors acting on it. The body is free because the diagram will show it without its surroundings. So you don't have to spend a bunch of time drawing trees and horses and the sun and all that sort of stuff. Just get right down to the object. Make it a box.
Mr. Bennett.
Graham.
Fire drill this period.
Oh yeah? How do you know?
Because I just got the text message.
From who?
Person saying there's a fire drill this morning.
Is there?
Yeah.
You have to tell me.
What are you, like, on the in or something? You're the inner circle? Mr. Casamat and you're like,
Can I go there myself? Come on.
No. No, you'll be perfectly fine. Let's get going then if we're going to miss some time.
The fire drill.
Okay. So here we have, okay, Lane, I really need to do this now.
Okay.
Let's take this picture to be a pictorial representation of a situation, a sled on snow with horses pulling it. First we'll represent the sled, the body of the problem as a really simplified figure. We just draw a box. Okay, most of the time, I'm just going to zip through this. You can read it on your own if you need to. I've read it 1,000 times. I know exactly what it says. Everything happens on Earth. So you should always draw in.
I think you're lying.
Most of our problems are going to happen on Earth. You can assume that gravity is there. So we're going to call that FW, weight force. Some books call it FG, force of gravity. Some say FMG, mass times gravity. There's a variety of ways to represent it. It all means the same thing. You have to be a little bit bilingual when it comes to symbols and stuff. Okay? I like FW. G is the acceleration due to gravity, and M is the mass of the carriage. There's also the normal force. Now, the normal force is one that prevents objects from falling into whatever it is they're sitting upon. It's always perpendicular to the surface, and that's important. Not so much for you guys now, but for grade 12, because when they're doing questions like where there's a ramp like that, the normal force isn't perfectly straight up. Okay? When your book is sitting on the table or your pull punch or what have you, gravity's down, the normal force is straight up, they're opposite. But on a ramp, which way is the normal force? It's not straight up, it's perpendicular, so it's at an angle. Okay? So, that's important for the future. Great.
We go with the front doors.
Yeah, front doors. Down those stairs, front doors. Meet me at the handicap parking sign and say, Mr. Bennett, I'm survived the drill, I'm here. For example, if there's a crate on the floor, then we say the crate experiences a normal force exerted by the floor, and because of this force, the crate does not fall into the floor. The normal force on the crate points upward perpendicularly to the floor. It's called the normal force because normal and perpendicular mean the same thing. So here's an example where the normal force is at an angle, and if you were drawing gravity there, it would be straight down, right? Now normally, pun intended, would you say that those forces are balanced? Would you say that the net force is 0? Yes. Would you say that these forces are balanced? Almost only counts in horseshoes and hand grenades. Are they balanced? They are not. So is there a net force? There is. And when there's a net force, there's an acceleration. So what happens to the box? Slides down the ramp. That's why boxes slide down ramps. Man, you're smart, Mr. Bennett. That's what you're thinking right now, right? No, you're not thinking that? Cool?
Not yet.
Oh, not yet. Okay. Let's add the normal force to our FBD. Do you guys have us draw like this?
Yeah.
Okay, awesome. Okay. Now, on the next page, friction happens just about everywhere. Unless it says that it's frictionless, or unless it doesn't say anything, then you can sometimes assume that things are frictionless. Things tend to go from left to right, just because that's our world, left to right. Maybe in cultures where they read from right to left, I don't know whether the friction goes the opposite way. Okay, so why do we have this FF here? What is that? Friction force. Okay? Which way is this object moving?
We don't know.
Why do you say that, Cole? We need more information.
Yeah, that always seems to be the answer.
Oh, so you just go with that. Nick says left. How come left, Nick? But does friction push all by itself? Like my hole punch sitting there right now, gravity's down, normal force is up. Is there friction acting on it?
Yeah.
Really?
No, it's not moving.
Friction only occurs when what?
An object is in motion.
Or trying to move it, right? Like if I try to move it, if I try to move it and I'm weak, I can't move it, right? Is friction there? It is. But if I take my hand away, no more friction.
Right.
So in this situation here, which way is the friction? To the left, right? So there must be, this is not complete, there must be someone pulling it to the right for friction to occur.
So it's going to the right.
We don't know that. What if the friction force and this applied force here were balanced? Well, then we get into that situation where if it was already at rest, then it stays at rest, like me pushing neatly on the hole punch. Or it could also be
In motion.
traveling at a
Constant.
constant speed. Well done. Could be traveling at a constant speed. Okay, so that's a push and pull. We would call that an applied force. This is an FA here. I'm giving you the simplified version of this. I'd rather than reading it all. Okay. It could be tension. Could be like from a rope. In this situation right here, I have FW down, FN up, FF to the left. What does the FF stand for? Friction force. So small f is friction, the big F is force. What do you think the FA stands for? Applied force. Is there a net force here?
Yes.
How do you know?
That arrow is vector.
This arrow is way bigger, and vectors, the arrow length of the arrow is a representation of the size. So this applied force is way bigger. Is it moving to the right? This one we can say yes. This one has a net force to the right. Correct? It's actually accelerating to the right. It's not just moving at a constant speed. It's actually accelerating. Seem easy enough? Let's try a couple together. The child next door wants to take his German Shepherd named Spot for a ride on his sled. He chases Spot, who's running away while dragging his sled behind him. What forces are acting on the sled? Well, there's our picture there. Here's the solution. Let's just do it sort of ourselves here. What do we need to draw in?
The dog.
Do we need to draw the dog?
No.
No. It's a free body diagram, free of all dogs and other animals. First step is usually weight force. You can draw it from the center if you wish. Some books like to do that. Some like to do it from the edge. It really makes no difference to me. Okay, so that's the weight force. Is this dog riding on a sled on the ground?
Yeah.
Yeah, so that means there's a normal force, Fn. Should those two arrows be approximately the same way? In fact, they should be exactly the same way. Am I going to get my ruler out and measure? No, I don't have time for that. If you can't make it, with the naked eye, if it doesn't look close, then I'm going to get my ruler out. Okay, but just make it close and it'll be fine. Okay, he's dragging the sled behind him. Does it say anything in the question about acceleration or friction?
No.
It doesn't. You okay there, Will? Yeah? Late night? It says nothing about acceleration, so we're going to assume that it's constant velocity, which means doesn't say anything about frictionless. Yeah, so I'm going to say friction force, applied force, and they should be equal. Bill, you need to wake up. Come on. Okay. They should be identical. Net force, total net force here is 0. Example number 2, Dot and Spot. Spot the German Shepherd is being walked by his best pal Dot the Siamese cat. I didn't make this stuff up. Actually, Dot is pulling Spot across the ice rink and disturbing the neighborhood hockey game. What are the forces acting on Spot? Now there's clues here. Secret code, if you will. Weight force. It's on Earth. Normal force. Because they say ice rink, that is secret special physics code for frictionless. Low friction. Okay? So I think what they want is just an applied force, if I'm not mistaken. Now that would mean that this time, what would be happening here motion-wise? What would it be doing? Nick says moving to the right, I think. That's right. But it would not only be moving to the right, it would be accelerate. Now you might ask, how can they accelerate when they're on a frictionless surface, right? Yes. It's one of those conundrums. They're wearing broom ball shoes. Special broom ball cat shoes. Could be. Okay. Let's talk about King Kong on the next page. While climbing the Empire State Building, King Kong peeks into one of the corporate windows and sees a poster of Tarzan swinging from a vine. Our furry friend decides he'd much rather be swinging from vines instead of hanging outside skyscrapers. When King Kong is swinging from a vine, what forces are acting on him? Well, King Kong, even though he's a fictional creature, still exists on Earth. Weight force. Can you think of any situation where there would not be a weight force? I'll just leave that one for now. Maybe there might be a space situation. Is there a normal force here? No. Why not? He's not on a surface. He's on a vine. So the upward force would not be a normal force. It would be a tension force. Don't get all excited about tension. Okay. Would they be balanced? Yeah, likely, yeah. He's just hanging there, right? No friction, no surface, thank you. Our furry friend King Kong has had enough of monkeying around, ha ha ha, and has returned to the Big Apple. Once again, he's up to his tricks with the Empire State Building, only this time he's taking the elevator. He's getting old. While he's riding up to the top of the building at a constant speed, what forces are acting on it? Well, again, Empire State Building exists on Earth. Weight force. Is there a normal force? Yes. Are they equal? He's moving up
At a constant speed.
at a constant speed. So what does that mean, Lane? He's not accelerating, so the forces must be? Equal or balanced. Excellent. Is there any friction? Really?
Elevator, yeah.
Well, but is there any friction on him? The box is King Kong, right? No, he's just standing there, right?
Yeah.
I mean, if the elevator was at an angle, there might be some friction or something or other, but it's not. It's going straight up and down.
Yeah.
Okay, you guys got this. No problem. Okay. Little pause. Not always. Does there always have to be more than one force? No. A book doesn't rest on a tabletop. Diagram the forces acting on the book. Weight force, normal force. They're equal to each other, right? That's the simple one. Girl is suspended motionless from a bar which hangs from the ceiling by two ropes. Diagram the forces acting on the girl. Weight force. Now, I think in the official answer key they show it like this. FT, two ropes. Now, what would you say about the length of those? They would have to be the same added together as this one, I think, right? Yeah. If you just had a single one, that would be fine too. I don't particularly think there's a need for both, but I guess maybe in some situations you might want both. So it would be something like that. That one's a little bit of a challenge, I suppose. Is there any sideways force?
No.
No. Monique, you're setting a bad example. Making me look bad. An egg is free falling from a nest in a tree. Neglect air resistance. Diagram the forces acting on the egg as it falls. Weight force. There's no friction. There's no normal force. There's nothing else. It's just free falling. As Tom Petty once sang, and then John Mayer ripped him off. It's just free falling. Flying squirrel is gliding, no wing flap, so just sort of coasting. From a tree to the ground at constant velocity. Consider it excuse me. I get pretty choked up.
Every time.
We got weight force. What else? Constant velocity means net force must be net force must be 0. So what would you call it though? It's not a normal force. R? Air resistance? Sure. I don't really care about the subscript. I would just call it friction force would be the way I would describe it. But it really makes no difference. If you want to call it F air or air resistance or R, it really makes no difference to me. The subscript is strictly a labeling thing. Now, some of you might say, but the thing is going sideways, right? Well, if you want it going sideways, then there is going to be air resistance sideways, but then it's going to be slowing down, isn't it? Because the net force is no longer 0. So that one's a little bit tricky.
There's no FBD.
There is no applied force. It's already in the air and moving, right? Remember, you don't need that applied force to keep it moving, right?
You could have a friction force if you slow down.
It would still have a component sideways and it would slow down. Like this?
Yeah.
But there would still be, I see what you're saying, Wyatt, but there would still, then, I guess it depends on what they're equal to, right?
Yeah.
Yeah, fair enough. I would say, if I were doing this, I think your best answer, what they really want, whoops, I'm pretty sure if I clicked on it, if I went back to the internet where I got it from, I'm pretty sure that's what it says. Okay, do you want to try these ones now?
Yeah.
Try those, I'll give you 5 minutes, and then I'll give you answers. A rightward force applied to a book in order to move it across the desk with a rightward acceleration. Consider friction, neglect air resistance. So it's sitting on a table. Weight force, normal force. There is friction. Friction always tends to be to the left. If you don't know, just put it to the left. Does it matter? No. There is an acceleration here, so it must be longer. Make it obviously longer. Don't make one millimeter longer than the other, hoping that I will pick the correct one. Well, he wants to be longer, so I can argue that. No, he wants them the same, I can argue that it's close enough. Don't do that, I'll mark it wrong. I know your game. Make it obviously longer.
Why did we do it?
Because you're going to do problems right away with this stuff. A rightward force applied to a book in order to move it across the desk at a constant velocity. This is going to be exactly the same, just
Equal at base.
everything's equal, right? Good. College student rests a backpack on the shoulder. It's motionless. Weight force. Tension force, right? Skydiver descending with a constant velocity. Consider air resistance. Weight force. F air or F friction. Constant velocity must be equal. Force applied to the right to drag a sled across loosely packed snow. That's code for friction.
I'll go.
Weight force, normal force, small amount of friction. There is acceleration, large FA. Okay, number 10 is the one we really got to talk about. This is the one that Will was asking about here. Football is moving upwards towards the peak after having been booted. It just has FW. It's already been kicked. The guy does not have the power of the force. He cannot apply a force to it. It's already kicked. You don't need to show the motion. There's only gravity acting on it. And it is. But that doesn't mean it can't accelerate it downward. When you throw the tennis ball up, I'm glad you asked. When I throw the tennis ball up, I throw it up, but the acceleration's down, which is why it slows down. If the acceleration wasn't down, what would it do? Keep on going. Now, does it matter whether I throw it straight up and down or whether I toss it at an angle? Which way is the acceleration? Still straight down, which is exactly what the grade 12 is doing. They're actually doing, what they're doing is, they're figuring out how fast it's going at the bottom of the ramp with the acceleration. They're going to figure out how much speed it slows down on the small jump ramp, and then they're going to make a prediction where it lands on the floor. And most of the time they get it right. It's pretty cool when it lands in the target. A car is coasting to the right and slowing down. Oh. Weight force, normal force, slowing down, just friction, right? Is there a net force here? Yes, there is. It's just friction. It's slowing down.
What if you need the friction longer than the acceleration thing?
There is no other force here, right? Now, we all know that if you take your foot off the gas in a car, there's still a little bit of push forward, right? Fair enough. If you want to say that, if you want that, I'll accept that. For that very reason.
That's what we did.
That's what you did?
Yeah.
I'm okay with that.
Anyways,
Okay. Awesome. We're making good time today.
well, I've been to a cafe.
Let's begin. Now, the key here is when you're doing these problems, start with a free body diagram. That's why we drew them. Okay, it helps your thinking. Lane, I know it's been a long morning, but try to refocus here. Constant force acts on a 12 kilogram mass and changes its velocity from 4 meters per second to 18 meters per second in 3.5 seconds. What is the force? So what are they really asking you for? The applied force. They're asking you for the applied force. What do we know? Now, some people like to write this stuff out. That's FA. The initial velocity is 4, and the final velocity is 18, and the time is 3.5 seconds. Some people like to write that out. That's fine. If you want to be lazy and you don't, that's also fine.
Where'd you get this sheet? Right? I never got one.
Did I put them all in my pocket?
Oh my
yeah.
god. Only 3 of the fun.
I only got oh no, never mind. I'm like, why did we get so many sheets?
Okay.
You know.
Now, the formulas that you're going to use are F net equals MA. Where did this one magically come from? F net equals FA plus FF. Well, what does F net mean? Jake, I know you know. No, F net. You answered the other day. F net?
Next.
Sum of all the forces, right? I think you said combination. Combination of all the forces. Now, you might say, Mr. Bennett, I thought FF was negative. Well, it is, okay? But this is the net force is the sum. You add up all the forces, but the value of FF is going to be negative. Lane, you need to watch, man, and concentrate. Yeah, I know, it's exciting. Tennis ball on the floor, or whatever you're looking at. I don't know.
I'm reading this.
Okay. I'm looking for FA. Which formula is going to be the last one I'm going to use? That one's going to be the last one. Okay? Do I know... Is there friction here?
Yes.
It doesn't say anything about friction, does it?
There's always friction.
There's always friction, but if it doesn't say frictionless, and it doesn't say there is a friction, only assumption that you can make is that the friction force is 0. That's the only thing you can assume. You can't just say, well, I don't know what friction is, so I'm quitting. Okay. So, before I can get FA, I'm going to have to solve for F net. In fact, F net, because FF is 0, the net force is the applied force, is it not? Okay, how do I get F net?
What's that mean?
FA is the applied force. F net is equal to m times A. I've got the mass. What do I not have? I do not have acceleration. That's where I start my solution at. Think backwards. A equals delta V over delta T. The acceleration is the change in the velocity divided by the time. We've done this already. Last unit. Delta V, 18 subtract 4. It went from 14 to 18. I guess some of you might want me to do this. Some of you might feel more comfortable with this. Delta V is VF minus VI. So that's going to be 18 minus 4, or 14. I think most of you can probably put 18 minus 4 up there in the delta V and figure it out. And what's my time? 3.5 seconds.
So is that, what did that say for?
18 minus 14. Those are the numbers that are given in the problem. Right? So 18 minus 4 is 14 over 3.5. The acceleration is 4 meters per second squared. Notice how I put everything in a nice line. I lined up my equal signs, and I wrote the formula.
You didn't really give us enough.
For me?
You didn't really give us enough.
I didn't give you enough room?
We got like a little.
Oh, I guess, yeah. I apologize.
Second one, you got lots of.
Yeah, I see that. Okay, now remember our plan here. What was the acceleration? What's the next step? F net equals ma.
No room for room. And that means meters per second.
The net force is the mass, which is 12 times the acceleration, 4. 48 newtons. Yup. Did we not agree that the net force was equal to the applied force? Yep. So what is the applied force? 48 newtons. You will notice that the problems are getting harder.
Yep.
This is where people got to start working. You got to practice these. Okay, so I found the change in velocity, I found the acceleration, then I found the net force, which is equal to the applied force. Okay, here's example 2. It's already written up there for you, right?
Nothing to diagram.
No, you might have to draw the diagram. A block is being pulled by a rope as shown. 25 newtons of force are being applied and the friction force is 5. What is the acceleration? The force applied for 4 seconds determine the velocity at the end of that 4 seconds. Okay. What's the plan? Let's lay out the path. To find the acceleration, what am I going to need to find acceleration? Do I have a mass? Oh, Mr. Bennett, this is what happens when you add in new questions. Okay, we're going to have to add in a mass. I'm just going to make it up. I'm going to say the mass is, wow, that's a little large. It's got to be kilograms too, by the way.
10 kilograms.
10 is good. Sure, let's make it 10. Make it 10. I apologize. I made a few changes and I guess I neglected the mass. Okay, so I've got the mass. How do I get the acceleration? What am I going to need here? I've got 25 newtons. This is my applied force, right? I'm applying 25 newtons. What's my 5? That's my friction force. What's the net? 30? Friction is opposite. 45? How'd you get 45?
No, I just add all the numbers together.
No, do not ever do that. That is the worst plan ever. The net force is the applied force plus the friction force, right? What's the applied force? What's the friction force? Minus 5. Giving me an overall net force of 20. And I think that should sit right with you, right?
Yeah.
Because the friction force is technically in the opposite direction. Remember all that stuff about left, right, positive, negative?
Oh.
Right? That's why we learn it in grade 10. Just so you can do this problem. So the net force is 20. To get the acceleration, F net is equal to MA 20 equals 10A. Good thing you picked 10 because now we can do it in our head. 2 meters per second squared. What are you plotting? How does that sit with you? Are you worried?
Yeah. That is dangerous.
We're trying to find the final velocity and we know the time.
Yes, sir.
Okay, so we've got here A equals delta V over delta T. The acceleration is 2.
Yeah.
Change in velocity, the time is 4. Delta V is going to be?
22, 8,
6,
5, 7,
7,
25,
1.
18, 62,
62.
4 times 2, 8. 3 by 4.
Delta V is 8. Is that the VF?
It's a change.
It's the change, that's right. So really, but we know the initial is 0, right? Do I need you to write all that down? No, I would be happy if you recognize, oh, hey, the VI is 0. If you just write VF equals 8, I'm good with that. I think that's a reasonable expectation.
Yeah.
Now, what if it had a velocity to begin with, right? Like, what if it was, say, like 6 already?
Then you wouldn't need to.
Then it would be 6 plus 8, right?
Yeah.
Okay. Okay.
No, we're done.
I know. I was. Can I do example 4? It's a 2-step one. But I'm not. I wouldn't do this if I was going to be here Monday. I promise I would. Yeah, I'll be here. This one's real short. In fact, here's what I'm going to do. I'm just going to write down the solution and then I'll answer it real quick. Okay, whatever, man. Should I give you the eye roll?
Yes. Think about Willis coffee cups and coffee balls.
Did I say F what?
F net. Yep.
Used to American jump gravity offers.
I wish I could. Okay. Real quick here. F net is 3150. Do I just add 250 or subtract 250? Okay. Here's where writing the formula will save you, because the vast majority of people do this wrong.
Mr. Bennett.
What?
Queens was on question 3.
Oh.
That's it.
4. Yeah, I
I was
skipped.
helping him out. Yeah.
Sorry about that, Jake. I skipped ahead, yeah. Okay, here's where writing the formula helps, because this F net is the 3150. Right? What are we solving for? The applied force. What's the friction force? Minus 250. And when you take it to the other side, you have to add it. Okay? And if you stop and you think about it, it makes sense. You need 3,400 newtons because 250 goes to what? Overcoming friction, and then the remainder, the 3,150, is used for accelerating. Okay? If you just always, I just subtract friction and I take 3,150 minus 250, you're going to get it wrong. You gotta write the formula. You got it.
Read.
Okay? I will stop there, I promise.
Read it up.